Hello everyone and welcome to our introductory video to fluid mechanics. In this video, we will be talking about the most important fluid properties to remember when we are dealing with fluid statics and fluid dynamics. We will start by defining the properties of a fluid. So what are fluids? In the most basic sense, we define fluids as substances that are capable of flow. So if a substance can flow, that is, it cannot hold its own shape, it can be deformed, it follows the shape of its container, and it always seeks out its own level, then that is a fluid. In our broad definition, we include both liquids and gases as fluids, but we can extend the definition of fluids to supercritical fluids and plasma as well. In our discussions, we will be characterizing fluids by their various properties, most commonly physical properties. The physical properties of a fluid are important for us because that helps us characterize what happens to a fluid when it is flowing or when it is at rest, and that is the foundation of fluid mechanics. Let us review the concept of temperature and how it affects fluids. By definition, temperature is a scale of how hot or cold a body is. Temperature can either be relative or absolute depending on its units. For example, degrees Celsius and degrees Fahrenheit units are relative temperature units, while Kelvin and Rankine are both absolute temperature units. When determining fluid properties, we are always using absolute properties, so you must know how to convert from relative to absolute units. For example, from degrees Celsius to Kelvin, you simply add 273.15, while for conversion from Fahrenheit to Rankine, we simply add 460. Temperature is very important in our understanding of fluid mechanics because it has a direct effect on majority of process variables such as density, viscosity, pressure, volume, and more. Temperature affects the properties of both liquids and gases. We will see later how temperature factors into our calculations for fluid properties. Next concept that we need to review is pressure. Pressure is basically defined as the force applied perpendicularly to a unit area. Pressure has little effect for liquids, but its effect is significant when it comes to gases. This speaks to the compressibility of liquids and gases. Even though both liquids and gases are considered as fluids, they are differently affected by pressure. Liquids are considered incompressible up to some extent. That means it takes a very large amount of pressure to change the density of a liquid. But for compressible fluids, such as gases, a small change in pressure can already have a big effect on the density of the gas. Pressure has varying effects on different types of fluids. Pressure is often measured by the use of barometers or manometers, depending on the mode of measurement. So the measurement of pressure by the use of manometers will be discussed in our lesson on fluid statics. As with the case with temperature, pressure also has two types. That's relative pressure and absolute pressure. The relative pressure in this case is what we know as the gauge pressure. The gauge pressure is measured relative to the atmospheric pressure. If we want to convert from relative to absolute pressure or vice versa, we simply use the formula absolute pressure is equal to gauge pressure or relative pressure plus the atmospheric or the outside pressure. The gauge pressure is often the pressure measured for a gas that is inside a container. That is why to convert that to absolute pressure, we still have to add the pressure exerted by the atmosphere on the container of the gas. For the calculations of fluid properties such as density, the absolute pressure is the one that we should use. Now let's talk about the density of fluids. Density is broadly defined as the mass per unit volume of a substance. It's the ratio of mass and volume. For a fixed amount of substance that is a constant mass, a change in volume would give us a change in density. For example, if a gas is expanding, the mass is constant but the volume is increasing, and since the density is inversely proportional to the volume, as the volume increases, the density decreases. So for a gas expanding, its density is decreasing. That's the same for liquids. If liquids are expanding, for a fixed amount of liquid, the volume is increasing, therefore the density is decreasing. That is the case for the thermal expansion of liquids. That's why the density of fluids is a strong function of temperature. Temperature affects the density of fluids. For liquids, the decrease in density as the temperature is increasing is evident in this graph. This is the density of water with respect to temperature. As the temperature increases, water expands, therefore its volume increases, so its density has to decrease. This is the behavior of density for majority of liquids. For gases, their density is a strong function of temperature and it's also a strong function of pressure because gases are compressible substances. For example, if you take a look at our equation for density for ideal gases, we have pressure times molecular weight divided by the universal gas constant R divided by the absolute temperature T. The density is directly proportional to pressure but inversely proportional to temperature. So for a fixed pressure and increasing temperature, the density would decrease because the gas is expanding if your temperature is increasing. But for a constant temperature and increasing pressure, you are compressing the gas, therefore the density is increasing. You will be encountering this equation for the density of gases throughout our lessons because the easiest assumption to make is that a gas is ideal. Of course, we can only use this for certain ranges of pressure and temperature. Let's proceed to viscosity. Viscosity is defined as a fluid's resistance to flow. You are already familiar with the concept of viscosity. If we say that the liquid is viscous, we say that because it flows slowly. For example, if we compare water versus honey, honey has a higher viscosity because it flows slower than water. If a liquid is viscous, that means that it has a large internal resistance to flow. The internal resistance comes from the friction between the molecules of the substance. For our lessons, we will be representing viscosity with the Greek letter mu. The viscosity of fluids are also functions of temperature and pressure, although liquids and gases behave differently for changes in temperature and pressure. For example, for liquids, the viscosity decreases as the temperature increases. That is because when the temperature of a fluid is increased, the fluid expands and the molecules of the liquids have higher energies and thus they can overcome the frictional forces easily. Less frictional forces means that the viscosity would decrease. For gases, they have the opposite reaction to an increasing temperature. As the temperature of a gas increases, its viscosity increases. That is because the molecules of a gas are already far apart even at low temperatures. By increasing the temperature of gases, you are increasing their energy and thus you are making the molecules move faster. If the molecules are moving faster, there is a higher probability of collision between molecules and that introduces friction between molecules. And as we know, if we have intermolecular friction, then that increases the viscosity of the substance. Remember this relationship. So liquids and gases have different reactions to temperature. What about pressure? Pressure has a very small effect on the viscosity of liquids because as we have established, liquids are generally incompressible for small changes in the pressure. Because of that, we can say that for incompressible substances, the viscosity is not affected by pressure. But for compressible substances, such as gases, an increase in pressure would result to an increase in viscosity, as you can see in this graph here. As you increase the pressure of a gas, you are bringing the molecules closer to each other, and thus you are increasing the probability of molecules colliding and introducing friction to the system. So the increase in temperature and the increase in pressure has the same effect on gases. They both increase the viscosity of gases. In general, density and viscosity are two of the most important fluid properties that we have to remember. Those are the physical properties often used in characterizing the flow of fluids. Now let's move on to process variables that are not related to the physical properties of a fluid. First, we have velocity. The velocity of the fluid is the backbone of everything involved in fluid dynamics, that is, the study of fluids in motion. We define velocity as the rate of change in the position of an object, in this case the substance, per unit of time. It tells us how fast or how slow a fluid is moving. For the applications of fluid mechanics, oftentimes, We are dealing with fluids flowing inside pipes or inside any other conduit, and the velocity paves the way for us to calculate the flow rate of your fluid. For fluids, generally, we have two types of flow. We have laminar flow and turbulent flow, as pictured here. As we discuss fluid dynamics and internal flow, you will be introduced to different concepts like shearing forces, frictional forces, pressure drops, and other parameters that are directly related to the velocity of the substance. So it is important for us to know what the velocity is. The important thing to remember is that oftentimes the velocity we are pertaining to here is the average velocity. The average velocity is also called the bulk velocity. And the value of the velocity can be used in determining flow rates. We define flow rates as the rate of flow of matter per unit time. The flow rates are directly proportional to the velocity. We have different ways of expressing flow rates. It can be in terms of mass flow rate, volumetric flow rate, or molar flow rate. Their only difference is what parameters are we measuring per unit time. So for mass flow rate, we are interested in how much mass is being moved per unit time. Volumetric flow rate is for volume, and molar flow rate is for the number of moles. Flow rates are measured by flow meters, which we will discuss in a future lesson. And here we have our general formula for the computation of flow rates. For the mass flow rate with the symbol small m with a dot at the top, we can solve that as density multiplied by average velocity multiplied by the cross-sectional area of the conduit. This is often the cross-sectional area of a pipe if the fluid is flowing inside a pipe. Alternatively, you can also convert between volumetric flow rate, which is capital Q, and mass flow rate by the use of density. So the mass flow rate is equal to density multiplied by the volumetric flow rate. And as you may have noticed from this first equation, the volumetric flow rate is determined by multiplying the bulk velocity of the fluid with the cross-sectional area of the conduit of the flow. These equations show us the relationship between flow rate and velocity. If you are given the velocity of the flow, you can compute for the flow rate. And if you are given the flow rate, you can compute for the velocity of the flow. That is a very important relationship when we discuss fluid dynamics. For now, let us apply our knowledge of the process variables involving fluids in answering these practice problems. First one, nitrogen gas exits a heater at a rate of 6 pounds per minute at 150 degrees Fahrenheit and 600 psi absolute. What is the volumetric flow rate of nitrogen? As mentioned earlier, the volumetric flow rate of fluids is defined as the bulk velocity multiplied by the cross-sectional area of the conduit. From our problem, we were given a flow rate that is 6 pounds per minute, which is a mass flow rate. The mass flow rate can be converted to the volumetric flow rate by multiplying it with the density of the substance. So we are going to use this second equation and directly convert the mass flow rate to volumetric flow rate. We just need to know what is the density of the substance. We have nitrogen gas, which we can assume is an ideal gas, and as such we can determine its density by the formula pressure times the molecular weight divided by the universal gas constant R divided by the absolute temperature T. We can directly substitute our given values in our formula for the density. That is pressure, 600 psi absolute, multiplied by the molecular weight of nitrogen gas, that is 28 pounds per pound mole, divided by R. Our R in this case is 10.73. The units are psi cubic feet over pound mole over Rankine. So our temperature should be in absolute units. We simply add 150 degrees Fahrenheit to 460 to make it Rankines. The density of nitrogen gas in this case is calculated as 2.57. The units are pound mass per cubic feet. By using this value of the density of the gas, we can now determine the volumetric flow rate of nitrogen gas. Rearranging our earlier equation, the volumetric flow rate is equal to mass flow rate divided by the density. Substituting, this is 6 pound mass per minute, that's the mass flow rate, divided by the density of the gas, 2.57 pound mass per cubic feet. If you take a look at the cancellation of units, pound mass would cancel. That would leave us with a unit of cubic feet per minute. Solving, that is 6 divided by 2.57. Our volumetric flow rate is equal to 2.34 cubic feet per minute. This example illustrates to us the conversion from mass flow rate to volumetric flow rate. Let's have the next example. A liquid stream containing only benzene, toluene, and paraxylene flows through a conduit that has a square cross-section. The total flow rate of the stream is 10 moles per second. The stream has the following composition in mole fractions: 0.3 for benzene, 0.5 for toluene, and 0.2 for paraxylene. The density of the mixture is 0.87 grams per cubic centimeters, and the conduit is 0.10 meters on a side. What are the mass flow rate and volumetric flow rate of the liquid stream? Enumerating our given, we have the molar flow rate, 10 moles per second. This is for the entire stream. We are also given the density of the mixture, that's 0.87 grams per cubic centimeter. You can imagine our system as a square pipe because it was mentioned that the conduit has a square cross-section. So we have a square pipe and your fluid is flowing inside of the pipe. The pipe has a side length of 0.10 meters. Let us tabulate our three substances. We have benzene. I will symbolize that as B, toluene, and the paraxylene. We are given the mole fractions. That is 0.3, 0.5, and 0.2. From the given mole fractions, we can then determine how many moles of the substances are flowing per unit second. So if we are going to assume the basis for every 1 second, we have 3 moles of benzene, 5 moles of toluene, and 2 moles of xylene. These values were determined by simply multiplying the mole fractions of the components with the molar flow rate of the stream. Now that we have the number of moles of the substances, we can easily convert this to mass and volume by using molecular weights and densities. We were not given the densities of the individual fluids, but we were given the density of the mixture. So what we can do is we can get the total mass of the substances and then we convert that to the total volume. For that, we need the molecular weight of the substances. These are in grams per mole. For benzene, we have 78.11. For toluene, 92.14. And for xylene, that is 106.16. To convert from moles to mass, we simply multiply the moles with the molecular weights of the substance. That leaves us with mass in grams. For benzene, that's 3 times 78.11. For toluene, that is 5 times 92.14. And for xylene, that is 2 moles times 106.16. From here, we can determine the total mass of the system. That is 907.35 grams. The total mass of the system can be converted to the total volume of the system by using the value of the density. To get the total volume of the system, we simply divide the total mass with the density. That's divided by 0.87 grams per cubic centimeter. Our total volume is 1042.93 cubic centimeters. Since our earlier basis is 1 second of the flow, that allowed us to use 10 moles as the total number of moles of the system. We can also use that to finally determine the mass flow rate and volumetric flow rate of the system. We simply say that the mass flow rate of the system is equal to 907.35 grams per second, and our volumetric flow rate is 1042.93 cubic centimeter per second. And that is how we convert a molar flow rate to mass and volumetric flow rates. Throughout our lessons in fluid mechanics, you will be encountering many problems like this, so it's important that we understand how to convert and use the different process variables. This is the end of the video. Thank you for listening, and as always, keep safe.